Hi everyone. Now this is the continuation from the previous section on the pressure, and I'm going to introduce you the idea of a barometer. Now the barometer is usually used to determine the atmospheric pressure of the environment. So for this part of the lesson, I'm just going to explain to you how it works and how it can be used to measure the atmospheric pressure. What we have here is a very simple setup. We have this very large container that contains a mercury reservoir. Right, contains a mercury reservoir, as the term already suggests, reservoir, a huge supply. And over here, we have the atmospheric pressure acting on the mercury reservoir. Note that we have a relatively long test tube inverted into the mercury reservoir, and also note there's no air in there. There's no air inside the test tube. It's inverted inside the mercury reservoir. And when the tube is slowly lifted up, inverted, it creates a mercury column. And once it reaches a certain height, there's an empty space. Now, note that initially there's no air in there, so the empty space has to be a vacuum. So for the rest of this lesson, I'm going to explain to you how this whole structure works, and it can be used to measure atmospheric pressure. Now, first of all, let's recap what we have to know. Now, recall in the earlier part of the lesson, P equals H rho G. So that's one of the very basic formula you must recall, pressure in a liquid. And in hydraulics, we also learned that pressure acts equally in all directions. Okay, pressure acts equally in all directions. So we're going to use these two we're going to put these two together to understand how we can use the barometer to measure the atmospheric pressure. When the atmospheric pressure acts onto the surface of the mercury reservoir, it acts in all directions and pushes up the mercury up the inverted test tube. Or we can say it pushes it up the barometer. So the mercury level in the inverted test tube rises until its weight acting on the cross-sectional area of the test tube becomes equal to the atmospheric pressure. I say again, the mercury level in the barometer rises until its weight in the column acting on the cross-sectional area of the tube becomes equal to the atmospheric pressure. At this moment, the space above the mercury column, it becomes a vacuum, and the pressure exerted by the mercury column the pressure exerted by mercury column becomes equal to atmospheric pressure. So I say again, the pressure exerted by the mercury column has now becomes equal to the atmospheric pressure. Why this can happen so? Because when the atmospheric pressure pushes against the mercury column, as indicated by the arrow, we need to take note. That's because pressure acts equally in all directions. Okay, pressure acts equally in all directions. So it pushes up the mercury until once it reaches a certain height. Okay, once it reaches a certain height, the pressure exerted by mercury column, which is this column, H, it becomes equal to the atmospheric pressure. So I'm going to erase some things here just to tidy up. So it becomes the pressure as indicated by the orange arrow by the mercury column becomes equal to the atmospheric pressure as indicated by the blue arrow. Right. So this is the same level. The pressure are equal. And hence you have pressure exerted mercury column equals atmospheric pressure. Now let's come back to the barometer again. The mercury column will rise to a certain height, and this height, when the space above this column is vacuum, this height is also known as the barometric height. And this barometric height has a particular value, approximately about 760 millimeters, depending on the location on Earth, and also depending on whether you are high on a mountain or underwater, or whether you're at sea level. So this 760 mm will vary a little. And hence, we can express atmospheric pressure Alright, ATM is the short for atmospheric, to be equals to 760. Now, sometimes we just want to read out the readings. We don't really want to go into intensive calculation. We just take 760 mm. That's the height of the barometer. And we add one more thing behind, Hg. Hg is the chemical symbol for mercury. So when we write 760 mmHg, we are actually telling the people this vertical height is measured using mercury. We can also write 76.0 cmHg. Less common, but can. Right, I already gave the reason. The length refers to the vertical height, and the chemical symbol refers to the chemical that you use to measure the vertical height. Sometimes 0.760 meters Hg, but this is more common. mmHg is more common. Okay, so now I'm going to show you how this 760 mmHg can be used to calculate atmospheric pressure using P equals H rho G. So the vertical height is 760 mm. We take it as 0.76 meters. Gravitational field strength 10 Newton per kilogram, and the density of mercury will be 13,600 kilogram per meter cube. So you don't have to memorize all these values, but once you're familiar with it, it just pops into your head. So P equals, you see this line here? Alright, pressure exerted by mercury column equals atmospheric pressure. So I'm just going to calculate the pressure of that mercury column, which will give me the atmospheric pressure. P equals H rho G, which is equals to H 0.76, rho 13,600, and then 10. and I'll get 103,360 Newton per meter square. This is the value of your atmospheric pressure. But in O levels, most of the time, so far, most of the time, uh, the exam questions tend to simplify into 100,000 Newton per meter square, or 10 to the power of 5 Newton per meter square, or 1.0 times 10 to the power of 5 Newton per meter square. So you're going to see this pop up very often, right? So that's how we are able to determine the atmospheric pressure.